In this video, we're going to learn about the disk/washer method of finding volume of rotation. So the idea in these problems is they're going to give us a shape in your picture here. So in this case, it's y equals x squared, and then y equals 0, and then x equal to 4. And you're supposed to look at all these and see what area do they enclose. And if I'll just redraw it here a little bit nicer. It's going to look something like this here. So they start with this shape in 2D, and they're going to take this shape and they're going to rotate it. In this case, they're rotating around the x-axis. Now, it can be kind of hard to imagine what's going to happen when you do that. When I'm in the classroom, sometimes what I'll do is I'll kind of cut out a shape like this at paper, and then you can attach it to like a little piece of a wooden stick or something. And then you imagine you're rubbing your hands and turning that piece of wood. And if you turn it really fast, you can kind of see this three-dimensional shape forming. That's what we're really doing here. So what's going to end up happening is going to go something like this here. And it's going to be essentially kind of like a horn shape, but with a solid interior there. And we're trying to find the volume of this. Well, what the disk washer method does is it says, okay, we're going to break up this volume by cross-sectional area, like in the previous video. So we're going to take a little random piece here at the point x, and whose width is dx. And we're going to look at what the little part of this shape is. Well, if your dx is small enough, the top is essentially flat, because it's infinitesimally thin here. And so what we really have here is a disk. This is a disk shape, and we know the formula for volume of this is pi r squared h. Right, it's the area of the circle times the thickness. So for a problem like this little miniature volume, well, what is my radius? My radius is going to be how far away from where I'm rotating to the edge of that shape. That's my radius. But if you look at our picture here, the edge of that shape is coming at the top of my graph, which is going to be, that means your r is equal to the y value there. And we know y is equal to x squared, so my radius here is x squared. And then my height, my thickness of this is my dx. Now, by cross-sectional rules, we're then going to integrate this for my volume. Based on this shape here, my x starts at 0 and goes to 4. And it's pi r squared h, so pi r squared. And then my h is dx here. And that's going to be pi x to the 4th, which is going to be pi over 5 times x to the 5th. From 0 to 4, and that's 4 to the 5th pi over 5, and then, what is 4 to the 5th? Looks like that's 1024 pi over 5. So that would be the volume of this kind of horn shape here. So in general, when you're trying to do this, you're rotating around the x-axis. The r value is really going to be the function value there. And then you go ahead and do pi r squared, and then the width is always dx in these problems. And then you get your answer. So that's how you find the volume of a rotation here. Now in this second problem, they change things up a bit. So we have y equals x squared, but we also have y equal to x. Now, unfortunately, it kind of looks small there. So what I'm going to go ahead and do is, instead of saying 1 happens at one place over there, I'm going to make it out at 4 here. So I'm still going to call it 1. So one of these is that every 4 is 1. Then 1, 2, 3, 4. It looks like this. So one of them is going to be y equal to x, and one of them is going to be y equal to x squared. So that is the shape that we are looking at. Now if we rotate this shape about the x-axis, we are going to get something like this here. So what we get is, we get the horn shape now, but now we're kind of missing, there's this empty part in the end. So imagine looking at the end of an actual horn, a trumpet, trombone, something like that. You do have empty space in there where the sound comes out. So this would be a more accurate representation of that. But something new is going to happen if I pick a little x value here and take a little width of it and try to draw the picture. Well, the top of it is going to be based on the y equals x graph, and we're going to have this nice disk here. But because of this part in the middle here, it's like a disk with a little circle cut out of the middle. And this is called a washer. That's why it's the disk or washer method. Basically, the washer is whenever you have this open area in the middle, and if it's solid, then you'd have the disk method. But otherwise, the same thing. Well, if I want to find the volume of this, it's pi r squared h, but the problem is you have the radius for the big part, and then you also have a different radius for the small part of this. So to avoid confusion, I'm going to call the big one capital R and the other one little r. And if I want to find the volume between them, I'm just going to take the volume of the big one minus the volume of the small one here. So it'll be pi big R squared h minus pi little r squared h. You take the whole disk and take away the part you cut out of the middle, which we can kind of factor out. It's pi big R squared minus little r squared h. And so in terms of an integral, it's going to be integral 0 to 1, because that's where our two things intersect each other. Pi, the big radius, if I tried to look at that over here, maybe purple. The big radius is the further one out. That's the y equal to x graph. So that's going to be just x squared. And then the little radius is the inner part. And maybe I'll use a different color for that one. How about orange? And it doesn't look that much better. But the inner radius here is based on the lower function, which is x squared and r squared there. So we get pi x squared minus x to the fourth, 1/3 x cubed minus 1/5 x to the fifth, 0 to 1 here. We're going to get pi 1/3 minus 1/5 minus pi times 0. And that will give me 2 pi over 15. So you see, this gives us the volume of this shape of the horn, but with the actual empty space in the middle. And that's the difference between disk and washer. Disk is where it's a fully solid object. Washer is where there's this inner emptiness in that you have to account for it by pi big R squared minus pi little r squared.